haere mai, ko te McNamara aho. It is a genuine pleasure to be able to introduce Rust to those of you who have sort of heard about this language and it's like, could you please stop? Rust has this notorious perception of being very difficult to learn. And this talk's job is to not teach you the language, but give you enough confidence for you to actually kind of make your way through the intro tutorial, or alternatively, to rapidly increase your Python program speed by being able to replace that one little bit with a native extension that you were too terrified to do because there was no way you were ever going to do it in C. Hi, my name is Tim. I like to do the boring bits like introducing myself right at the end and start with, I guess, the more interesting thing. So we're going to be discussing some of these really difficult concepts like lifetimes and borrowing and kind of and also how on earth a programming language like deals with not having exceptions, which are actually quite easy. We're then going to build a native extension live on stage, and then I'll do the boring bits, like introducing myself and so forth. Okay, so to start with, we actually need to explain the term memory safety, because this is kind of Rust's big claim. There are other languages that are just as fast, like C or C++ run essentially as fast as you can write. You could write assembly. The idea is that with C++, this idea was that we had zero cost abstractions. That is, you could not write assembly code faster than the functionality that C++ would provide. And Rust actually adds one more thing, which is this memory safety component. And I'm going to embarrass myself, I guess, by saying that here's a definition that I think is kind of useful. Memory safety is a guarantee that whenever you ask for a value, it's like I've initialized a value A, and I go back and do something else, and then I come back and ask for A again, that A will still be there. And that is a surprisingly difficult assertion to be able to guarantee before your program even runs, irrespective of threading, irrespective of, let's say, I/O or the kernel. Like the operating system is going to kind of play around with your memory however it wants, and yet Rust is able to do this without any runtime performance overhead at all. And that is why it's being looked at into the Linux kernel. That's why it's being adopted into the Windows kernel. That is why Azure is being, parts of it are being written in Rust. That's why AWS rewrites their components in Rust. And it's actually something that everyone in this room and everyone in the recording benefit from as well. As long as you have to kind of get through this kind of horrible, pedantic problem. So I want to explain, there's a Python program, we initialize a variable A, and then we kind of delete it, and then we ask for it again. Or we assign it to something else. What happens? We get an error. Which name error? Oh, sorry, which name error? Sorry. Which error? Name error, correct. And moreover, this happens at runtime. So whenever you accidentally assign something to none or delete it, you might get a name error or something else that looks like an attribute error, and A is not defined. Now, this is an error that is impossible to ever happen in a Rust program. There are other errors that are also impossible to ever have. You can never confuse the difference between assignment and equality. And there are many, many others. Here is a subtly more complicated Python program. I'm importing the threading module, and I want to do something similar but different to what we just did before. But I've got some sort of analysis around different cities where coffee is brewed, and I've discovered that Wellington's coffee is actually much better than, say, Sydney, Melbourne's, Auckland's, or Christchurch coffee. I mean, And by the way, there is no such thing as a strong flat white for anyone anyone who's been to Australia. Every flat white needs to be double shot. Excuse me, sorry. I am a Wellingtonian, by the way. So we want to print this analysis out. Like here's our magical report, and we're going to do it in a subthread. And that's actually, so we run it, and Wellington, that works perfectly fine. We've actually spawned a new thread. In the child thread, we've gone and printed our thing out, and that's access to global variable, or at least a variable defined in the main thread. So wonderful. Now we're going to introduce a little bit of complexity. Just for the space, I've had 3 imports here. Here's the same report, except we add some space, some time. Maybe we're going and fetching some records from a database. We might be going and accessing something. And so essentially, we're adding some non-determinism in there. Then we print it out. Same thing. We start going. But in our main thread, we also sleep. And by the way, there's the typo. This is analysis. We join on our worker thread, and then we run it. What happens there? It works, right? Yay! Or it might break. We don't know. In fact, we could never know. And yet Rust has this ability to somehow warn us against this. So the borrow checker we can conceive of as like a component within the Rust compiler that actually kind of goes and inspects kind of logical time. It kind of almost has this mathematical analysis of the way that execution is occurring, and will guard against this kind of problem. So essentially, one way, if you've ever used C++, is that you know that every dereference will always succeed. Or if you've ever used Java, null pointer exceptions will never occur. Or Go, the null pointer exception is just not a thing that Rust programmers have to worry about. And in Python, that's attribute error. It just doesn't exist. With like a very important asterisk that there is an escape hatch to be able to do things, but we won't worry about that. I'm sure someone will at the end of the talk. Feel free to ask me about unsafe later. But how does the borrow checker work? Well, it works by the fact that in Rust, variables don't just have a type or a name. That's what we're used to in any reasonable programming language. A variable has a name and a data type, right? In Rust, it also has this other thing called a lifetime. And, well, what is a lifetime? A lifetime is essentially the span of time where accessing that variable is allowed. It is mostly, but not quite aligned to lexical scope. And I can show you an example of we're going to look at some Rust code very shortly, which doesn't compile and is extremely confusing for newcomers because it is like this it's essentially a fishhook in the language while you're developing a mental model about what is, actually happening. But first we need a slight diversion. Can anyone guess what this is? Coffee shops is like so good. I don't know if there are many coffee shops on Kapiti Island. Kapiti Island is kind of this bubble off to the left-hand side. So these are sightings of the kurura, a native penguin species that you can go and visit at Wellington Zoo, by the way. And uploaded into iNaturalist. There was also an iNaturalist talk yesterday. And so we're going to do some more data analysis, or not really. So we've got some data type penguin. And we have hoiho. Hoiho come primarily from, I guess, they're arranged now as kind of Dunedin era, Dunedin through the Catlins down to Invercargill to the southeast coast. Korora would have a much wider range, and so they're in Wellington Harbour. And Tawaki, they're more on the Fiordland side of the South Island. So they're also known as, so Hoiho is the yellow-eyed penguin, Korora is the little blue or little penguin, or in Australia also known as the fairy penguin, and Tawaki is known as the Fiordland penguin. So we've got our little Rust program. Oh, haha, we have our sighting of a Korora. Wonderful. And we print it out. If we try and execute this and run this, we get a couple of warnings. So let's find out. Let's actually go and explore what's happening. Here's the playground. And I can run this thing. We get a couple of compiler warnings. Rust is very pedantic and is kind of fussy about unused variables and so forth. And so it's going to kind of complain about it. But here's the output from the program down at the bottom. We actually get so there's our sighting. Now here's the bit that really confuses beginners and non-beginners, to be honest. We'll add another sighting. So what we have here is an instance where I'm essentially moving the place where I am allowed to reference from the original variable name, sighting, to the next variable name, another sighting. The Rust compiler sees this reassignment and says, what you're doing here is you're saying that you no longer need to ever access the original variable name. So now, logically, responsibility for that data has essentially shifted. And the term that Rust uses, which is inherited from C++, but what Rust uses is move. So if you have used a systems programming language before, you'll understand the distinction between move semantics and copy semantics. Rust will use move semantics by default. If you don't know what the last 30 seconds or 20 seconds, just ignore. That's fine, that's fine. But we get this kind of horrible error message. You borrow a move. Like, what is a borrow? It's assignment. It doesn't mean anything. What does it move value? I don't know. I just reassign something. And as a beginner, you get more than this. But this is what it looks like. You just kind of have these kind of shining red lights and this interruption of mental flow. And my hope is that this is not a signal that your code is somehow incorrect. It's a signal to you that you're learning. And that's actually okay. So let me kind of go through this in some more detail. So here is the new code. I'll run it and invoke this horrible error message. So we get another thing about an unused variable. We can sort of ignore that. And this is the line that I highlighted in the code. But look at what else Rust provides. So we get a very specific error message. This is exactly the problem that I have detected, and it's saying that here are a couple of ways out. So one of the ways that we could, it says here that one of the things that I could do, it's another way of it saying, this move occurs because the sighting has type penguin, so the variable has a data type penguin, which does not implement the copy trait. Now, in Python terminology, or closer to Python terminology, a trait is an abstract base class. It's not quite the same. Traits are a little bit more kind of knitted into the fundamentals of the Rust programming language. However, you can say that, well, it doesn't behave like a copy type. Instead, we use Rust default, which is this move semantics. So essentially, we're yanking the ownership of the original variable name into this new variable name. Another way out, so it sort of hints here that we could implement the copy trait. Otherwise, if you implemented the clone trait, so some other interface, another base class, you could actually clone it. Now, I wonder if I can show this in code. So here is a new file. And we're going to call this penguins.rs. And I'll just copy this and hope that it works. It's unlikely to work without problems, but that's life, doing things live. Because I want to show you what it means to kind of wriggle around these error messages. So here is my code. I don't have a lot of information from the language at the moment. The editor is very confused because I don't have a proper project set up or anything like that, but here is my code. And I can invoke the Rust compiler manually by, actually I'll just double check where I am. Yeah, I'm inside the right directory, so I can invoke the Rust C compiler and go penguins.rs. And I get the same thing. We get this horrible yuck thing about a copy and cloning, la la la. So let's try our first way out. So the first suggestion was to implement clone. And it turns out that if you have, let's say, an enum, we can ask the compiler to implement that base class for us with this derive, essentially kind of sort of like a decorator, but not quite. It acts at compile time. And now I add a clone method. I'll still get the warning about an unused variable. However, no output is actually produced, which means the compiler is happy, and I can now invoke penguins, and I get my output. So that's one way through. And it, just to confuse you a lot, and again, this is one of the things that you will run into as a beginner, is that we can actually ask Rust to do the same thing with copy. The abstract base class, though, acts in a subtly different way. It's essentially purely protocol-based. If you have a type which implements copy, then it will implicitly be duplicated in memory. And it will sort of, quote, just work. So here's my warnings, la la la, and now it's the same output. The reason why this is very confusing is that when you start dealing with Rust, you will start with numbers. It's very natural to start with integers. They implement copy. So you will reassign things. There will be no problems at all. As soon as you start to deal with more complex things like the rough equivalent of a list in Python or a string, things of unbounded length, essentially, those cannot be defined as copy by the compiler, and so you will suddenly have these borrowing issues that will suddenly start to kind of entangle you. Cool. Now, let's move forward, because I do have a couple of other things to chat about. Rust doesn't have exceptions, so kind of like, what does it have? Well, instead, every single thing that could generate an error returns a result, which is a value. Now, that's kind of odd, because we think of errors as something which kind of interrupt what's going on and allow me to kind of work through the Rust mentality. If you genuinely encounter something which is unable to be handled, essentially your program will crash. That's the only out. So what is this thing that is this? We'll start with option, because conceptually an option, which is, it's essentially equivalent to the typing optional type in Python's type hints. You can think of none or some or as being just a class of error that means nothing. And we'll stick with that because this capital T is a type variable, which we can bolt into anything. Here is my class of some sort of collection class where I contain some items. And inside that, I want to define a last method. Now, if my list items is empty, I should return none. This is something that is pretty natural to, this is something which feels very odd for a Python programmer to even think about, because idiomatic Python, you would raise index error if you tried to access the last element. And in fact, there's special handling for -1, la la la, but if, in Rust, we don't have that. So here is something that is approximately similar. We have some collection which contains items, and we want to implement that. So implementing means bolt on methods onto the type. So you can actually have multiple implementation blocks. The right angle braces on the left-hand T just means that I get to choose what I call my generic type. And so we're using the same number, the same variable in the same place. And now I get this kind of difficult bit with references. I need read-only access to the self variable inside the method. Last, and I return an option of a reference to T. If you think of the Python code, ignore the Rust just for a second, and think what happens when you actually return an object out of a list from a function. What you do is you're returning back a reference into self.list and actually assigning a variable to the element inside there somewhere. That doesn't worry Python at all, because it has what is known as a garbage collector, which will actually ensure that the problems that Rust tried to prevent never occur. Python does that at runtime. Rust doesn't have a runtime. So that's option. Now, result is something that is a little bit more complicated. Inside a result, we could just imagine that we had an enum. Actually, I'll keep going with penguins. Let's say we're just doing some scientific experiment, and we have an enum, which is like an outcome. We might have success or failure. And yet, we want to be able to parameterize these outcomes with some sort of type T. But we also want to be able to be more broad than just saying there's one type of error. So actually, there's two type parameters. There's T and E. That's all Rust is. In fact, that's how Rust's result is defined in the standard library. There is no more complexity than that, except you kind of get a bit scared because there's two type variables in here. In fact, I've got the syntax wrong. This is actually supposed to be square, but let's accelerate. Let's try and write an extension module in about 4 minutes. No pressure. Okay, so a Python extension module can be implemented in Rust, and let me show you how this works. So here is the code. We're going to be following along the demo, just to show you that it's actually, they didn't lie. If they did, and I'm going to embarrass myself very quickly, I apologize. So we want to make this string sum. It's going to take two variables, and then it will add them up and return it back as a string. This doesn't exist on, oh gosh, my time continues to tick. I feel, like I've, going to activate this. And we want to pip install Maturin, which is a very strange name for a very useful project. It's a bit weird. Maturin, so what do we want to do? We've got a couple of different binding options. We're actually just going to pick Pyo3. CFFI is the oldish one. Unify is a nice one. And we don't need to worry about all the rest of that. Let's look at what we've got. we've got a little project that looks a bit like a Python project and a little bit like a Rust project. We can now go into our Rust. And, oh, there it is, right there. Ha-ha! Oops. Okay, and now let's start a Python interpreter. What this is going to do is go and fetch all of the depositories from the equivalent of PyPI for the Rust, which is known as cargo, crates.io. It is then going to compile the code and expose it to the Python interpreter as a Python module. Hello. We can now, Python here is the Python interpreter that is specific to the virtual environment. Go away. And I can import string sum. And now I can actually add two numbers together, which sounds like very trivial, but actually is kind of cool because we've actually gone and compiled Rust and exposed it to Python, and it works. Well done. So that's Pyo3. Now a little bit about me. My name is Tim. I run a consultancy training organizations and teams about Rust and Python. The kind of consumer side is a thing called timclicks.dev. But previous to going out on my own, I worked as the global lead of Rust education at AWS, as well as a couple of other bits and pieces as well. So I'm based here in New Zealand, and I'm also hosting a Rust conference this week, next year.
Sorry, I didn't mean to loom quite so ominously. We do have time for a couple of questions. So who wants to receive the cube of questioning first? Anybody? Oh, nice short throw for me.
So you have a number of options when you start up that Matchroom project. How would you compare them?
I would go with Pyo3, it's easiest.
Nice, succinct. Anybody next for the cube?
Those different options, by the way.
Oh, there's, I don't.
Hands up, or even stand up if you want to receive
Someone
the
up the
question.
back, Tom really wants to throw this as far as he can.
I'll just ask the question.
Yeah,
there's a question up there.
There is a question. Hey, you can just ask.
Go along, you can do it.
Oh, God.
Oh, that was so close.
Have you got an example where the different language features, like the different lifecycle handling between Rust and Python, get in your way and you've got to jump through hoops?
Yeah, so the difference, it kind of ties into the previous question. If you want to do some really complicated gymnastics, like initialize a value in the Python interpreter, pass that to Rust, manipulate it there, you need to be able to tell Rust that it cannot delete the thing, otherwise Python is going to get very confused. And so it's typically transitioning through that boundary is where the problems will be. And the general answer that you tell Rust is you just say, it will last for the length of the program, which has got this very weird name called the static lifetime, which is inherited again from the systems programming terminology, which kind of relates to the static area of memory and the virtual address space. If anyone wants to go down that rabbit hole, it's a fun dive.
All right, we have one over here. Another long throw. Oh, that was, and that is why it is padded.
Yeah.
Can you give a few examples of where you might use Pyo3, or have you used it yourself?
Yeah, so I was a data scientist for a long time and learned Rust as a Python developer. So another part of my history, I was the previous conference director about a decade ago of Python, KiwiPyCon, and was worked as a data scientist, but we had to do terabytes and terabytes of data processing, but there were some very heavy loops that we wanted to, essentially I looked to Rust because Python was way too slow, and would sort of kind of randomly get name errors in places. And so a typical example, if you've got some long running service like a web server, and you need to dispatch to something else very quickly.